Welcome to Camo Monster Shell and Tube Heat Exchanger Design Part 2. In the last part, we have calculated the area of the shell. The next step is the calculation of shell equivalent diameter. It is based on the layout of the tubes that show the configuration or arrangement of the tube inside the shell. For literature review, you can visit chapter number 6 and 7 of process heat transfer by DQ current. From these two formulas, like we have here the triangular layout of the tubes, so using this formula we have putting pitch is equal to 1.25 inch, which is 1.25 over 12 feet. So d naught is equal to 1 inch 1 over 12 feet. So putting these values in this formula for triangular layout, we calculate the D equivalent, that in this case here is calculated to be 0.202 feet. The next step is calculating the shell side film coefficient. It is actually the same as we have done in the tube side film coefficient calculation case. Everything is same, only the difference will be here we use the D equivalent diameter of the shell. Remember, do not use the inner diameter of shell. You have to calculate equivalent diameter and use it here. And if you do not use it, it will cause a much error in the calculation of the heat transfer coefficient. So here we have calculated the velocity, because here we do not have iterated it like we have iterated in the tube side. It comes out to be using the same formula, G over density. This is the area, mass over area, mass over area. This is again our 2-second conversion. This is the density of shell side fluid. Using the Prandtl number mu Cp over K, it comes out to be 5.56. In this case, again we have seen the Reynolds number is far greater than 4000. Oh, it is miswriting, it is actually greater. So we will again use the same formula for the calculation of the heat transfer coefficient, and it Hi will come out as defined before in the last video. So here we will not correct anything, because the inner shell heat transfer coefficient will make importance, and the outside will be air, and it is outside of the heat exchanger, so we do not have to do anything with that. So it is correct and effective, Hi inner shell heat transfer coefficient. Now for overall clean coefficient of heat transfer, we have to multiply Hi naught multiply H naught and divide by summation of Hi and H naught. So we will calculate here the clean overall heat transfer coefficient. The purpose was to calculate the heat transfer area for the heating zone. So dividing the Q, remember the unit consistency check will be important here. This Q is in BTU per hour, because it is in BTU per hour and it is per feet square. So the overall answer of AC will be 12.1 feet square in this case. So unit consistency check will be important. Q over U delta T. This is LMTT, corrected LMTT. This one is 263. Now for the design overall heat transfer coefficient, which is UD, involves the dirt factor. This is the factor A. It has been taken from the literature reference, feet square per linear feet. It depends upon the shell side layout and parameters. It depends on many functions. It is taken from the literature out here, 0.1899 feet square per linear feet. The total surface can be calculated by multiplying the total area with the factor A and then multiply by tube length. The tube length has been taken here as 16 feet, as the larger heat transfer is being taking place, so we selected 16 feet. Now UD will change because the area has been changed. Before we use the heat transfer area, now we have used the total surface area, which is quite larger. So UD, the value of UD is always far lower than the value of UC. You can see UC is equal to clean overall heat transfer coefficient is equal to 259.49 BTU per feet square hour degree F, while UD is equal to 85.34. There is large difference between them. The difference will show us the dirt factor, how much dirt is being there, how much fouling is being there, that have reduces the UC to a value of UD. So the dirt factor can be calculated by the ratio of UC minus UD over UC multiply UD. There is a mistake, it is UC minus UD. So in this case it comes out to be 0.007. The criteria has been defined in the chapter number 6 and 7 of process heat transfer of the three regions: low fouling, high fouling, and moderate fouling. I think it is in the moderate fouling region. You can check the literature reference. The last step is the pressure drop calculations. Now it can be done in the two ways. One is by using the formulas of fluid mechanics, like you can distribute the pressure drop into drag force or skin force, skin friction factor or drag friction factor, both. You can also use the word of force for it, but the problem is the heat transfer geometry is not sustained in those calculations. For the heat transfer calculations, you have to use the pressure drop formulas that are defined in the chapter number 6 process heat transfer by DQ Kern. So first of all, you have to find out the Reynolds number that we have calculated above during the calculation of heat transfer coefficient. Now we have to use the Moody's chart. Moody's chart is easily available on the internet, and from assuming a relative roughness factor of your selected metal or material, you can calculate by comparing the friction factor on the left side of Moody's chart come out to be, in this case, 0.1016 feet square per inch square. The LD is equal to 0.25 multiplied by 16, which comes out to be 4 feet LD. The number of crosses are n plus 1 is equal to 12 LD over B. B is the baffle length. It is 8 inches in this case, and LD, the effective length, is LD, and it is 4 inch in this case. And number of crosses, number of times the fluid crosses the baffles, is 6 in this case. So average molecular weight of the stream, it is average molecular weight, not of the component. If you have multi-component mixture, the same method that has been defined before in the video, mole fractions multiply by molecular weight of each component, and you have to calculate the average molecular weight to use it. Now specific gravities. For using the specific gravity for the cases of vapor, you have to divide by the density of air. In the cases of liquids, you have to divide your stream density by the density of water as a reference. So in this case, specific gravity comes out to be 0.36. The diameter of shell is 1.94 feet. Equivalent diameter is 0.202 feet. Using this equation, we can easily calculate by putting all the data. Here the pressure drop comes out to be 0.716, very optimum. We have to keep it in the region of 1 to 10 psi. More than can cause a problem. Using the tubes, for the tube side calculations, we use the same formulas as before, but in the shell side, the velocity the kinetic part of the pressure drop do not have much importance, as the velocity is low. We have seen here, and phase change is also involved, another factor. So that in the tube side, there are two factors that are involved. First is based on the same as defined before, the skin, and the second one is based on the kinetic force, the kinetic energy. The formula is defined here, and you can put the values of velocity, g, specific gravity, and specific gravity in the tube will be different. Formulas are same. So we see here that the pressure comes out to be 27 psi. It is far greater than the 10 psi. The range we defined is crossed. So you do not have to worry about, because there are two ways in which you can reduce that pressure drop. One is to reduce the baffle spacing by reducing the baffle spacing, you can change this value, number of crosses. So here delta P will be reduced, but it is not that much optimum and good. The second technique is using the split flow. The split flow will divide the velocity into half. So V will become 10 feet per second from 20. So again putting this, and we will get far lower, 6.90 psi. So the total pressure will be in the optimum range, 7.87 psi, safe region, smaller than 10 psi. Now the data has been put. There are two important things that we have missed in the whole lecture. The one is the calorific wall temperature. Sometimes you have, imagine when you have cooking a food, some kind of, you think the outer wall of the container is hot while the fluid become cold. So there is always remains a difference between the wall temperature and the actual temperature of the fluid flowing inside the tube. So the wall temperature of tube and the temperature of fluid, that are both important factors to consider, and the difference between those must be averaged to a proper value so that the heat transfer coefficient comes out to be a correct value. Here we have a chart from the process heat transfer by DQ current, page number 857, and from that you need the API gravity oil. The API gravity of oil specifically defined because the difference that calorific wall temperature will cause the calculations will be only the viscosity correction. You will see in the formula viscosity over viscosity at wall exponent 0.14 is equal to 1 in the most cases if it does not need any type of correction. But if there is a boundary layer on the tube inner surface or outer surface, you need to correct the exchanger with this viscosity correction factor, and you have to calculate the mu W at the calorific wall temperature. So in such scenarios, the calorific wall temperature calculation is much important. But in the case where the non-viscous fluids are involved and deviation from isothermal flow during heating or cooling does not introduce an appreciable error in the calculation of heat transfer coefficient, it does not have any much importance. Therefore, most of the time it is ignored in the calculations, but the importance of this must be considered. The next we have missed is the property tab. In the properties, I have defined that we can use we can multiply the mole fractions by density of individual components to find a cumulative density. But it is not always the case, because in the viscosity, like for example in the viscosity for solutions, the average density of the solution will be 2 times the viscosity of the liquid. However, the salts are involved, but there is a formula set to multiply mu naught. Like for example, the viscosity, for calculating the viscosity of average viscosity of mixture, we have to use the mole fraction multiplied by individual viscosity multiplied by molar mass square root molar mass, additional factor to be multiplied and divide here. So it depends upon the type of system and nature of system that how the properties will be averaged to find a cumulative single value. But again, the beauty of heat exchanger design, like shell and tube or double pipe, is you have to only need these properties to find the heat transfer coefficient. It really does not depend upon how much components, how many types of component, it is slurry, solution, everything you have, everything or whatever you have, you only need these 4 to 5 parameters. Okay, this is enough for today, and the heat transfer design, heat exchanger design section is completed. The next we will come out with the heat exchanger design with phase change, in which one fluid will be involving the phase change with latent heat absorption or disruption. Thank you.